First part, as I mentioned, we'll talk about assay transfer and how we effectively transfer an assay between labs. Transferring an analytical procedure, which is sometimes just abbreviated to TAP or method transfer, is a documented process. And it's about qualifying a laboratory to use an analytical test procedure that has originated at a different site or a different laboratory. The idea of this is to ensure that the new laboratory has the same procedural knowledge and as well as training and ability to perform the transferred procedure as it was intended, and to the same level of at least the same level of performance as the originating laboratory. This is described in USP 1224, transfer of analytical procedures. It's a bit of terminology that we'll be using. So we'll be referring to the sending unit, which is also known as the transferring unit. And this is the site or laboratory where the analytical procedure originated. It's often where it was developed. The receiving unit is therefore the new laboratory where we're going to be transferring the method to. There are several approaches to this. The most common and the approach that we deal with the most, I would say, is probably the comparative testing approach. And this is where we perform testing at both sites on the same lots of the target material, and these are batches that would be from standard production. And can also just be a single batch, or it can be multiple batches. But these can also, comparative testing can also be done using some intentionally prepared samples, such as for an impurity test, you might look at spiking in a particular known amount of an impurity into a sample and see if the new laboratory can detect that same impurity. We can also carry out co-validations for assay transfer. This is where, whilst the originating laboratory performs a validation, the new laboratory is included in the validation procedure. So the sending unit involves the receiving unit in a sort of inter-laboratory validation procedure. So they become part of the validation team, and as well as having then data that shows that the assay has been validated at both places, we're also generating data about the reproducibility of this assay between the two sites. And then we've got complete or partial validation solely at the receiving unit. This is this functions as a normal validation. Whether it's a full or partial validation depends on whether there is some justification that some elements do not need to be repeated. Off the top of my head, I can think perhaps specificity is perhaps an example of this. Once you've demonstrated it during your initial validation, you may not need to repeat it. However, you equally may need to complete a full revalidation. It just depends on the situation. Transfer waiver is the last, and essentially this is a get out of jail card. This is where under particular circumstances where the receiving unit is deemed qualified to start working on the analytical test procedure without some sort of comparative or validation procedure in place. This does need to be clearly justified and documented. It's not something that we get involved in as statisticians, but just to be aware of that this is a possibility. It tends to be where there is particular knowledge of a active component, for example, of a drug in the receiving laboratory. When we set up a study for assay transfer, we need to set acceptance criteria, and these will be based on the performance of the method from historical data, such as stability and release testing results. And if available, they should also include some sort of comparability criteria for results from other sites. We can also derive these acceptance criteria using statistics based on the difference between mean values and established ranges, and they should be accompanied by an estimation of variability, particularly intermediate precision of the at the receiving unit, and or use some statistical method for the comparison of means for the assay result. So we'd look at both comparability in terms of the results, such as the relative potency at both the sending unit and the receiving unit. And we'd want to look at acceptable variability at the receiving unit. Just a note from USP 1224 here that we can actually just use a single batch of our product or testing material for the transfer. And the reason for this is because we're not trying to comment on the manufacturing process itself, but rather evaluate how the analytical procedure is performed at the receiving site. So in terms of setting an acceptance criteria on comparability, when we're looking at the reportable results at both the sending unit and the receiving unit, we would consider something like this, where we'd have the relative potency at the receiving unit and the relative potency at the sending unit for a given sample, the same sample, in fact, or same batch of sample. We could then calculate the ratio of these relative potency values for each sample. And a ratio close to 1 in this case will indicate that we have more comparable results. So we might be either side of 1, but the closer we get to 1, the more comparable they are. And we're not just going to do this for a single sample, but we would use multiple samples, even if they are from the same batch, so that we can generate a bit more information. We would then calculate a 90% confidence interval for the ratio. And this is like what we've done in equivalence testing before and discussed for that. We use this 90% confidence interval because it's equivalent to 2 one-sided tests at the 5% or 95% level. And because we're looking at relative potency values and we're looking at this ratio, we would look at we would be working on the log scale. So we'd actually have the log of these ratios here and the 90% CI for that ratio on the log scale. And then we would have to predefine rather, before starting the study, some acceptable limits. Commonly, we would want these to be symmetric on the log scale. So for example, we could go for 0.9 to 1.1 or 0.85 to 1.25. We can also just set our own limits relative to what's acceptable for the assay or for the given assay transfer. But we do also then need to look at the variability, because that will give us some understanding of how the test site, the receiving site is functioning. So we look at the set some criteria on the acceptable variability at the receiving unit. The most sensible way of doing this is to look at the percent GCV, or percent geometric coefficient of variation. So this is similar to the coefficient of variation, except we're looking at log scaled values. So we would look at the percent GCV of the log relative potency values for all samples, or for all independent replicates of the same batch. We can also use a variance components approach to look at the variability, or if we have multiple lots of the same batch, we can do a pooled estimate of our percent GCV. And then, as before, we would set some predefined limit for this variability. And we can either set this on the value of the percent GCV itself, or on the upper 90% confidence interval of this. We only look at the upper limit because obviously if our receiving unit has better precision, that's perfectly acceptable. In terms of the number of samples that we want to test at the sending and the receiving units, we're not. I'm not going to go into too much detail here, because the sample size calculations for assay transfer can get quite complicated, and it also depends on what information is available about the assay and about the sending and receiving sites. But there are a few areas that we can think about, and we'd have to make assumptions on in order to do some sort of sample size calculation. So firstly, we have the intermediate precision at each site. This is mentioned in the ICH guidelines, but they talk about between site variability, and this isn't particularly clear, because when they are referring to between site variability, they're actually talking about the intermediate precision at each site. But this can get quite confusing when we're talking about variance components, because we could particularly pull out the site level variability, but that's not quite the same thing. So they're talking specifically at intermediate precision at each site. Comparability is another thing that we have to consider, which is basically, firstly, how comparable do we think the sites will be, and how are we going to measure our comparability, and what do we mean by comparability in this situation? Is it our relative potency values, for example? Then we also have our acceptance criteria, and this has an impact on the number of samples we want to, or we will need to use. If there's not much data available, then we generally suggest going with a set of limits such as 0.85 to 1.25, and use a sort of iterative approach to see what sort of sample sizes you would require to achieve that, because this also impacts on the required probability of success. And this can also have an implication on the number of samples. So we can end up doing a sort of, like I say, an iterative approach to deciding on the number of samples as well as the acceptance criteria. So in essence, we're trying to say, right, well, if we have this level of, if we want to achieve this level of acceptance, how many samples will that take? Okay, well, that's too many, so we're now going to have to either use a different method, or we're going to have to change our acceptance criteria in order to meet reasonable sampling procedures. Or if we end up with a really high sample number, we have to then actually consider, is it actually less work to just do the full validation in and of itself at the receiving unit? So it's only really if we can minimize based on information that we have and statistical sample size calculations, the number of samples that we need to do for our comparability assessment, whether that's actually worthwhile instead of just doing a complete validation. So it's always best to kind of look at the two options and how many samples will be required for a full revalidation, how much work that is. Recapping on what we've just discussed. So often when we're trying to move from an assay from one site to another, or from one lab to another, we want to do this with as kind of in the most streamlined way possible, and ideally we would probably like to avoid revalidation, as this is often quite laborious. So we've discussed the idea of the sending unit and the receiving unit, and that we need to check the comparability, such as the 90% confidence interval on our ratio of relative potency estimates at the receiving site and the sending site. And we'd also talked about the variability at the receiving unit, and we're looking at our measure of percent GCV of our relative potency estimates. And we want that to be set below a limit, or we can set the confidence interval of that percent GCV below a certain limit as well. Are there any other questions on this first part? Okay, so the second part of this discussion, we're going to look at reference bridging, and hopefully you'll see why we've grouped these two topics together. There's quite there's some similarities here in terms of the procedures that we go through, and in terms of trying to establish the same assay performance. But we're also going to discuss why we need to change reference standards at all, and how do we avoid revalidating our assay when we do change reference standard. And we'll look at that through the reference bridging study. So the reference standard itself, as we've discussed, is pretty critical to bioassay, because it's necessary to have a reliable material against which we're going to test our test samples, so that we can accurately quantify our relative potency. And the reference standard itself will have some sort of or we can assign some sort of level of specific activity of the 100% potent reference material. So we could consider this the sort of absolute potency, and we can use this to actually then assign a absolute potency value for our test sample batches. So that would be by multiplying the relative potency of our sample by the reference potency sort of label value, as it were. The specification limits for batch release will depend, or for stability testing, will depend on the potency of the reference standard. That is going to affect how ultimately, because of our relative potency measure, it's going to affect our whether or not our test sample meets our specification. So where possible, a standard should be representative of the samples that are going to be tested in our bioassay. And testing should be performed to qualify a standard, should be more rigorous than just general routine testing for lot release. In a fairly conventional approach to reference standards is to have a sort of two-tiered approach, which I'm sure some of you will be familiar with. So we have our primary reference standard, which is often the batch that we're early on in development we set aside as our sort of gold standard, and subsequent standards can then be prepared using the current manufacturing process to establish working standards, and these can be used then throughout the assay's life cycle, and we can use the primary reference standard to qualify our new working standards. It's fairly common as well to have separate procedures for establishing either the reference standard or the primary standard or the working standard, because sometimes our manufacturing process can be different when we are at the point of running a routine assay and wanting to generate a new working standard to when we first established our primary reference standard. And that is covered within USP 1032. So why do we need to replace the reference standard at all? Well, gradual changes in the activity of the reference standard can lead to some potential bias in relative potency measurements, and it can also lead to a loss of similarity with our test samples. So we highly recommend that we think about changing our reference standard, or how to handle changing our reference standard early on, even during development, and definitely before you actually need to, because we can't necessarily predict when our reference standard might degrade or no longer be fit for purpose. Or we might even just run out of our reference standard itself. The material isn't going to last forever. So the USP specifically comment on this, and they say that it's important to think about this in advance and to archive aliquots of our reference standard batch, our primary reference standard, so that we can assess comparability with later standards down the line, and also investigate assay drift. And this relates back to the idea of assay monitoring. So the only way that we're going to understand whether or not our assay is changing is if our working reference standard is something is changing in our current assay and our working standard is moving with that, then actually if we compare back to our kind of frozen, stored away primary standard, then that might actually give us an indication that we've seen some sort of drift. We'll have a look at what the impact of a change in the reference standard material could actually be. So in this plot here, we've got our standard 4PL dose response, and we've got our primary reference standard in dark green, and we've got a test sample in orange. When we calculate the relative potency for this test sample, which we're going to call the relative potency old, or in relation to this old reference standard, we're going to give that a relative potency value of 41%. We then introduce a new reference standard. This might be a working reference standard, or it might be something to replace the current reference standard. This is shown in light green, and it's almost on top of the old reference standard. So when we calculate the relative potency of the test sample using this new reference batch, we have a slightly different relative potency. So now our relative potency with the new reference standard, RP new, is 44%. And this is because both the test sample and the new reference lie slightly to the right on the dose response curve to the compared to the old reference standard, i.e. they're both less potent. So the test sample and the new reference standard are closer together in relative potency than the old reference and the test sample. In this case, it may be the other way around. And what we can understand from this is that if we compare the two relative potencies from the old reference and the new reference, our new reference standard would have a relative potency of 93% relative to the old reference standard. And we can calculate that from the ratio of these old and new test sample measurements. However, we don't have to use the test sample as a comparative tool. We can do a direct head-to-head comparison of the new and old reference standard. So in this case, we can ignore the orange line and just look at the green ones, and we would say that we're going to treat the new reference standard as a test sample and calculate the relative potency directly. And we'd then repeat this multiple times because, as ever in bioassay, we wouldn't make decisions based on a single plate. So in this case, again, we measured the relative potency and it's 93%. So we repeat that a few times. First time we get 101%. It's slightly higher. Then we go down to 79% and then 92%. So this is building up a picture of the new reference standard and how it's and its potency with respect to the old reference standard. And it also gives us an idea of the bias, how far from our target 100% this new reference standard lies. Ideally, we would have a new reference standard that is the same as our old reference standard. It's 100% potent, but that's not necessarily going to be the case. So we're also wanting to understand the variability in these measurements between our repeat measures of our new reference standard, because that's going to tell us how much our measurements are moving around the average and give us an overall idea of the precision of our estimate of the new relative potency. When we replace our reference standard, we want to try and avoid having to revalidate the entire assay. And as I mentioned, that's about being able to demonstrate that the assay is still able to perform as expected to the same level of performance that we achieved previously. So just in the same way with assay transfer, now we're looking at a change in the reference standard material, but it's the same idea. So now what we're going to do is have a look at the potency of the new reference standard relative to the old reference standard. So what we can calculate is something called the offset, which is almost like a percent recovery. And ideally, that percent recovery would be 100%. The offset will be 100%, which would indicate a one-to-one relationship between the old and new reference standards. However, if this isn't the case, then that offset value can be used to indicate the potential bias. So if we don't calculate this offset value and we don't understand the differences between our old reference standard and our new reference standard, we can end up in a situation where test sample measurements will be biased because we've just applied this new reference standard and we haven't thought about how different it is to our old reference standard. So firstly, we could end up with unnecessary batch rejection. So we'd be wasting resources because our test sample measurements might lie outside of the specification limits. Or we might have a case where our test sample batch actually now falls inside of the specification limits when it shouldn't do, which would lead to inappropriately accepting a new batch, which could lead to it being incorrectly dosed or releasing something that shouldn't be released in the first place. So this offset value is going to be really helpful for understanding the differences between test sample measurements once we've changed reference standard. So as I mentioned, the offset can help us amend our newly calculated relative potency values so that it's consistent with the measurements that we would have seen with the old relative potency, with the old reference standard batch. So the way we do this is the measurement that we get from our test sample with reference to our new reference batch, which is our RP new. We multiply that by our offset value, and that gives us the relative potency for our previous batch. So if you think about that first example we saw, if we only have that new reference standard, but we also have our offset value, then we could calculate the relative potency of the test sample to be 44%, and then use that offset value of 93%, which is the reference standard in relation to the old reference standard, and we could calculate our relative potency of 41% with respect to the old reference standard. So using this offset value allows us to consistently compare against the specification limits that were established when our old reference standard was in place. In order to quantify what that offset value is, we need to make multiple measurements of the batch that is going to be the candidate for the new reference standard. So we need lots of replicates of our new batch versus our new reference standard versus our old in order to determine the offset. And in some cases, the QC sample is actually people using their assay is actually also what's being lined up as their next working standard or their next reference standard to replace their primary reference. So you might already have this data. So we're going to take a look at this example where we do have that. So if we have this two-tiered reference standard approach, then we might use our QC sample as the new reference, and we're always going to be collecting data about that next working standard. So we get all this data from our QC sample, and these are our relative potency values. We have 114 values here for our new reference batch, and based on all of this information, this is a great amount of historical data. We would be able to calculate a good estimate of our average relative potency for the QC sample. So we would calculate the geometric mean of that relative potency and the confidence interval around it. So that's the geo mean is based on the mean on the log scale, and that gives us a value of 98.7%. So we're almost within 1% of the old reference standard. To give us an idea of how much data we might have need to collect in order to conduct our reference standard qualification study, we'll have a look at just the last 20 values. So if we were to do this and only use 20 values for our head-to-head testing on our study design, if we were to say that we're going to treat these last 20 values as our test samples and we're going to do our head-to-head comparison of our old reference standard and our new reference standard, then we would get an average of 96.8% and a slightly wider confidence interval here based on these 20 values instead of the 114 that we had previously. So this gives us a slightly different mean and confidence interval, and based on this, our offset value would actually be closer to 3% away from the old reference standard. So we do want to be able to get a reasonable estimate of the relative potency of the new reference lot, and we want to get a precise estimate of that. But how do we figure out how much data we need? So we'll need to generate some new qualification data in a specifically designed study. And we're going to have pairs of or test samples of the new batch versus the old batch. So we're going to have to do some sample size calculations. And this will depend on the standard deviation of repeated measures of the same relative potency. So in other words, this new reference standard batch repeated multiple times. So from earlier, you'll perhaps remember that the variation of a log relative potency value for a single replicate of a sample within a single run is calculated based on the sum of the inter and intra assay variances. For the qualification study, we want to know how many runs we'll need to conduct and how many plates that we should include in each of those runs. So what we're going to do is we're going to look at what this would entail for study design for K runs, including N plates. And the way that we would do this is we want to have a look at our 95% confidence interval for the average of the relative potency across all of our bridging and reference or reference qualification data. So we can write this 95% confidence interval in such a way that it's dependent on both the number of runs, so k in this equation, and the number of plates, which is our n, within each run. This formula here that we've described, it comes from the USB guidance, and for our study design, we're going to have a look at using something called the critical fold difference, which is the latter part of this equation. We're going to look at more of this in the next slide, but the critical fold difference is essentially the ratio of the upper limit of the 95% confidence interval divided by our estimate of the relative potency. So it gives us a measure of how wide our 95% confidence interval is around our estimate of relative potency. The formula that we see here is essentially an approximation. This is a formula that's recommended, and this approximation is recommended by the USP. And it's given by this log relative potency value, which is our mean log relative potency, plus or minus 2 times the square root of this variance calculation, depending on the number of runs and the number of plates. So, for example, we will assume that we've made the decision for the design of this new relative potency qualification study that we're going to use 3 plates in a single assay run. And this is just so that we can simplify things for this example. We can vary the number of plates as well as the number of runs, but it's simpler if we just keep the number of plates static, and we'll have a look at how the number of runs affects our estimate of precision. We also, before we start, need to have an initial estimate of our inter-run and intra-run variation to get us started with these calculations. And often these values of inter and intra run variation are established from our intermediate precision assessment that we do during validation. We can also obtain these from, for example, that QC data that we might have about our new reference standard, though. And we're going to be working on the log scale here. So I mentioned this critical fold difference. So our estimates of intra and inter-run variability can be used to determine the size of differences, or the fold difference, that can be distinguished between samples tested in a bioassay. And we can think of this critical fold difference as essentially as the half width of the 95% confidence interval of an estimate of our log relative potency. So the critical fold difference between reportable values for 2 samples that are tested in the same runs of the bioassay is given by this formula for k runs with n plates, where n is going to be 3. And we use this value of 2, which is an approximate 2-sided critical value for the normal distribution. So this value of 2 is given by the USP. It represents some approximation of the normal distribution used to calculate a 95% confidence interval for the log relative potency. We could replace this value of 2 with a t-distribution with the correct number of degrees of freedom, but USP recommend this approximation, so that's what we're going to use. So this gives us our critical fold difference, which is related to that half width of our confidence interval. And we can then use this to calculate our 95% confidence interval around our log relative potency estimate. So we get this log of our critical fold difference plus or minus with the log relative potency. And as I mentioned before, the way that this relates is essentially that we have, for relative potency on the raw scale, our critical fold difference is essentially the 95% upper limit divided by the relative potency estimate. So how does this affect our precision? Assuming that we have these 3 plates per run, we're going to look at how the precision is impacted by the number of runs. So we pop these numbers into the equations, and what we see is as we increase the number of runs from 1 all the way up to, in this case, 20, there's no reason that it has to be 20. This is purely just to exemplify the rate of change of the precision. We find that the critical fold difference starts to decrease, and it initially decreases very rapidly. And as we've seen previously with the use of replication to improve precision, we do start to see a tailing off of the rate of change. So the more runs we add, the less of a change in our critical fold difference that we see. In other words, we get more incremental changes in our precision as we add more runs. But what this graph and what this information can help us do is inform the appropriate number of runs that we will need to obtain a certain level of precision. For example, 10 runs might be quite good here because we've got down the kind of the steepest part of the slope here, so we've made big gains in our precision, but after that we're not going to see that much improvement by repeating the number of runs more and more and more. But it does depend what we're going to try and achieve in terms of our critical fold difference. So remember that because this is a ratio of the upper confidence limit to the estimate, with 10 runs, we're essentially saying that the upper limit is 1.04 times bigger than the estimate. So this might be acceptable level of precision for assessing our new reference standard, but it equally may not be, and that's going to depend on other factors, on the kind of probability of success, perhaps on acceptance criteria. So that's going to have to come from a further statistical evaluation, or it may be simple enough to just pick a value for the number of runs. It's also worth considering that we've only looked at runs here, but we can also vary the number of plates. And as we increase the number of plates, we're also going to see a decrease in precision. And it can also be the case that sometimes we have more variability within a run than between runs. So if that was the case, then we'd prioritize increasing the number of plates over increasing the number of runs. But we haven't investigated that further here. So some other considerations that we need to take into account for the new reference standard and how we set this up is that system suitability criteria may need to be revised once we have our new reference standard in place. And that's because the model parameters for our reference standard could change. In addition, the criterion for our relative potency of our QC sample might also change because it's no longer relative to the same reference standard. So if we were going to reassess our system suitability criteria, we'd want to again have a certain number of runs with our new reference standard on our QC. We've suggested here more than 10 runs in order to make an assessment of what our new system suitability criteria should be. We also have to consider whether or not the assay needs validating, or if we can suffice with a bridging study between the two reference standards. And it's always worth considering the fact that once we replace a reference standard, or if we continue to replace reference standards in a sort of consecutive fashion without having a primary reference standard to refer to, then we can lead to a sort of an accumulation of errors and a gradual drift away from our original absolute potency, as it were, original starting point. So if possible, it's best to have that archive or the sort of stored samples, aliquots of our original primary reference standard in order to compare whenever we produce a new reference standard batch. And the other thing to bear in mind is that our old reference standard, the one that we've got stored away, may itself drift. So we need to be quite careful when choosing an offset value for our new working reference standard. And again, this is where assay monitoring and in combination with stability testing comes into play. So we need to, there's a lot of things to take into account here when considering reference standards, and they can be quite tricky things. So rounding up on this, there are many reasons for replacing your reference standard, such as it being depleted or expired, or that there's some evidence of degradation, as shown in stability testing. There may also be, we then need to calculate the relative potency of our new reference standard in comparison to our old reference standard. This gives us our offset value. And we can either compare using test samples or a direct head-to-head comparison. And we can improve the precision of our estimate of the new relative potency of our reference standard by both increasing the number of runs and the number of plates that we use to test. However, wherever possible, we want to minimize the number of runs so that obviously waste our reference standard material. Are there any questions on the reference standards?